Imagine holding in your hands a piece of rock and ice that's older than our entire solar system. A cosmic time capsule that has traveled through the void between stars for over 7 billion years, carrying secrets from when our galaxy was young. On July 1st, 2025, we found exactly that, and it's heading straight toward our sun. July 1st, 2025, the night we found something impossible. Picture this. It's just past midnight in the Atacama Desert of Chile. While most of the world sleeps, 4 robotic telescopes are methodically scanning the sky, their cameras clicking away every 60 seconds. These aren't just any telescopes, they're part of the Atlas Survey, humanity's most advanced early warning system for dangerous asteroids. But tonight, they're about to discover something far more extraordinary than a space rock threatening Earth. The Atlas telescopes operate like cosmic security cameras, photographing the entire visible sky every single night. Each image captures an area 100 times larger than the full moon, and sophisticated computer algorithms compare tonight's sky to last night's, looking for anything that moved. On a typical night, they'll spot dozens of known asteroids, maybe discover a new one, and occasionally catch a comet awakening as it approaches the sun. But at 12:47 a.m. Chilean time, something appeared in the constellation Sagittarius that made the computers pause. The object was moving, yes, but not like anything in their vast database of 1.3 million known solar system objects. The trajectory was wrong. All wrong. Dr. Larry Deno, the Atlas Project scientist based in Hawaii, received the automated alert at 6:47 p.m. local time. After 15 years of hunting asteroids, he's seen thousands of discovery alerts. Most turn out to be space junk, known objects, or computational errors. But this one made him sit up in his chair. The preliminary orbit calculation showed an eccentricity of 6.1, a number so high it shouldn't exist for anything bound to our sun. When I first saw those numbers, Deno later recalled, I thought our software had glitched. Objects in our solar system can't have eccentricities above 1.0 unless they're from somewhere else. Within 6 hours, observatories across 3 continents were turning their telescopes toward this mysterious visitor. The Mauna Kea Observatory in Hawaii, the European Southern Observatory in Chile, and the Palomar Observatory in California all confirmed the same impossible thing. This object was moving too fast and in the wrong direction to belong to our solar system. By July 2nd, just 24 hours after discovery, the Minor Planet Center Astronomy's official record keeper issued Electronic Circular MPEC 2025-N12. The designation was historic, 3I/Atlas. The I stands for interstellar, making this only the 3rd confirmed visitor from another star system in human history. But here's what made this discovery truly remarkable. Unlike the previous 2 interstellar visitors that caught us by surprise and disappeared before we could study them properly, 3I/Atlas was still months away from its closest approach to the sun. We had time, precious time, to study a messenger from the stars. The global astronomy community erupted. Within hours, #InterstellarVisitor was trending on social media. The SETI Institute pointed their radio telescopes at the object just in case. The European Space Agency started calculating whether any of their missions could be redirected for a flyby. NASA's Planetary Defense Office confirmed it posed no threat to Earth. It would pass safely at 85 million miles away. But the most stunning realization came from the spectroscopic analysis. As telescopes around the world captured the faint light reflecting off this cosmic visitor, something unprecedented emerged. This wasn't just any interstellar object. Based on its trajectory and composition, 3I/Atlas appeared to be over 7 billion years old, a fossil from an era when our galaxy was less than half its current age. Dr. Robert Weryk, the astronomer who first spotted 1I/Oumuamua in 2017, summed up the feeling perfectly. Finding one interstellar object was extraordinary. Finding 3 means we've opened a new window into the galaxy. But finding one this old? We're literally touching the ancient history of the cosmos. Meet 3I/Atlas, the largest visitor from another star. So what exactly is 3I/Atlas? Imagine a mountain-sized chunk of cosmic ice and rock, roughly oval-shaped and somewhere between 1 and 11 kilometers across. To put that in perspective, if it turned out to be 11 kilometers wide, it would be larger than Manhattan and potentially 10 times bigger than our first interstellar visitor, Oumuamua. But size isn't what makes 3I/Atlas special. It's what it's made of and where it came from. Unlike Oumuamua, which appeared completely inert and showed no signs of the ice sublimation we'd expect from a comet, 3I/Atlas is very much alive. It's spewing water vapor and dust into space, creating a coma, a fuzzy cloud of material that extends up to 24 kilometers across. When astronomers first captured images of it through powerful telescopes, they could clearly see this ghostly envelope surrounding the nucleus, proof that ancient ice was finally awakening after billions of years in the cosmic deep freeze. It's breathtaking, says Dr. Kelly Fast from NASA's Planetary Defense Coordination Office. We're watching water ice that froze when the universe was less than half its current age finally start to sublime as it feels the warmth of our sun for the first time. The spectroscopic analysis, essentially analyzing the fingerprint of colors in the light reflected from 3I/Atlas, reveals a composition that tells an incredible story. The object shows clear signatures of water ice, the same H2O molecules that fill our oceans and flow from our taps. But it also contains traces of carbon monoxide, methane, and complex organic compounds that formed in the frigid outer reaches of some ancient planetary system. What's particularly fascinating is what 3I/Atlas doesn't show: signs of heavy processing by cosmic radiation. Objects that spend millions of years in interstellar space get bombarded by high-energy particles that should alter their surface chemistry. The fact that 3I/Atlas appears relatively pristine suggests either it hasn't been in interstellar space as long as we think, or it was protected by its own outgassing during previous close encounters with other stars. The color analysis reveals another clue about its origins. 3I/Atlas appears slightly reddish, similar to objects in the outer regions of our own solar system. This suggests it formed in the cold, distant regions of its home star system, far from its parent star where water could freeze solid and remain stable for billions of years. But perhaps the most remarkable thing about 3I/Atlas is its activity level. As it approaches our sun, it's becoming more and more active, losing an estimated 10 to 15 kilograms of material every second. That might not sound like much, but over the course of its journey through our solar system, it will shed roughly 100,000 tons of ancient interstellar material, a cosmic gift that scientists are racing to analyze. Dr. Frank Marchese from the SETI Institute explains the significance. Every molecule of water vapor, every grain of dust that 3I/Atlas releases carries information about conditions in its birth system billions of years ago. We're essentially doing archaeology on a galactic scale. The size estimates come from observing how much sunlight 3I/Atlas reflects and comparing it to its brightness. Based on its distance from Earth and the amount of light we detect, astronomers can calculate its approximate diameter. The range of 1 to 11 kilometers reflects uncertainty in its exact shape and surface reflectivity, but even the conservative estimate makes it significantly larger than Oumuamua's maximum dimension of 400 meters. What makes these size calculations even more impressive is the technology used to detect 3I/Atlas in the first place. At the time of discovery, it was shining at magnitude 18.5, roughly 4,000 times fainter than the faintest star you can see with the naked eye. The fact that our robotic telescopes can automatically spot and track something so dim while it's still over 500 million kilometers away demonstrates just how far our cosmic surveillance capabilities have advanced. The numbers that prove it's alien. Now, let's talk about the numbers that absolutely, definitively prove 3I/Atlas came from another star system. In astronomy, we don't just take anyone's word for extraordinary claims. We need the math to be bulletproof. The smoking gun is something called orbital eccentricity, and 3I/Atlas has shattered every record we've ever seen. To understand why this matters, imagine throwing a ball in the air. No matter how hard you throw it, if you're standing on Earth, that ball will follow a curved path and eventually come back down. That's because it doesn't have enough speed to escape Earth's gravity. The same principle applies to objects orbiting the sun. Planets move in elliptical orbits with eccentricities between 0 and 1. A perfect circle has an eccentricity of 0, while a stretched-out ellipse approaches 1. Even the most extreme comets from the very edge of our solar system, Those coming from the Oort cloud have eccentricities just barely above 1, maybe 1.001 or 1.002. 3I/Atlas has an eccentricity of 6.141. That number is so far beyond anything naturally possible in our solar system that it's like claiming you threw a baseball and it reached the moon. It simply cannot happen unless the object originated from somewhere else entirely. But wait, it gets even more incredible. That eccentricity translates to a hyperbolic excess velocity, the speed the object had relative to the sun when it was infinitely far away, of 58 kilometers per second. To put that in perspective, that's over 129,000 miles per hour, or fast enough to circle Earth in just over 3 hours. Dr. Davide Farnochia from NASA's Jet Propulsion Laboratory, who specializes in calculating the orbits of these interstellar visitors, puts it in stark terms. When we plug 3I/Atlas's position and velocity into our orbital mechanics software, the computer essentially says, this object doesn't belong here. The only way to get numbers like this is if something was accelerated to these speeds by a different star's gravity well. The trajectory tells us even more. 3I/Atlas approached our solar system from the direction of the constellation Sagittarius, arriving with a velocity that was tilted at a steep angle relative to the plane where our planets orbit. This isn't the gentle, shallow approach we'd expect from something that originated in our solar system's distant Oort cloud. This is the trajectory of an object that has been wandering between the stars. When astronomers trace that trajectory backward, accounting for the gravitational influences of all the planets and the sun, they can calculate where 3I/Atlas was millions of years ago. The answer is mind-bending. It came from the direction of the galactic thick disk, a population of ancient stars that formed when our galaxy was young. But here's where the detective work gets really interesting. By measuring exactly how 3I/Atlas's orbit changes as it approaches the sun, astronomers can determine whether it's experiencing any non-gravitational forces. And indeed, they've detected a tiny but measurable acceleration caused by the comet's outgassing. As water ice on its surface sublimates and jets away into space, it creates a rocket-like effect that slightly changes the object's trajectory. This outgassing acceleration is actually crucial for confirming 3I/Atlas's interstellar nature. It proves that what we're seeing is real cometary activity, not some measurement error or unknown force. More importantly, the direction and magnitude of this acceleration are consistent with a comet that's experiencing our sun's heat for the first time in its multi-billion-year existence. The precision of these measurements is staggering. Astronomers can determine 3I/Atlas's position to within a few hundred meters. Even though it's currently over 400 million kilometers away, they can measure its velocity to within millimeters per second. This level of precision comes from combining observations from dozens of telescopes around the world, using techniques refined over decades of tracking potentially hazardous asteroids. Dr. Alan Fitzsimmons from Queen's University Belfast, who has studied all 3 confirmed interstellar visitors, emphasizes the certainty of these measurements. The orbital determination for 3I/Atlas is based on over 200 observations from 15 different observatories across 4 months. The math is unambiguous. This object is not gravitationally bound to our sun and never has been. 7 billion years old. Reading the cosmic fossil. Perhaps the most mind-blowing aspect of 3I/Atlas isn't its size or its spectacular orbit. It's its age. When astronomers study the light coming from this cosmic visitor and compare it to what we know about stellar evolution and galactic dynamics, they arrive at an almost incomprehensible conclusion. 3I/Atlas is likely over 7 billion years old. To understand what this means, let's put it in cosmic perspective. Our solar system formed 4.6 billion years ago. Earth itself is 4.5 billion years old. The oldest evidence of life on Earth dates back about 3.8 billion years. When 3I/Atlas first froze into its current form in some distant planetary system, our sun didn't even exist yet. Our entire corner of the galaxy was just a cloud of gas and dust waiting to collapse under its own gravity. How do scientists determine the age of an object floating through space? It's like cosmic forensics, piecing together clues from multiple sources. First, there's the trajectory analysis. By working backward from 3I/Atlas's current path and accounting for the gravitational influences of stars it has encountered over its journey, astronomers can estimate how long it's been wandering between star systems. The math suggests a travel time measured in billions of years. But the real smoking gun comes from understanding where 3I/Atlas originated. Its trajectory points back toward the galactic thick disk, a population of stars that formed between 7 and 14 billion years ago, during the early epochs of our galaxy's history. These ancient stars have chemical signatures that reflect the universe when it was much younger, with fewer heavy elements and different conditions for planetary formation. Dr. Amaya Moro-Martin from the Space Telescope Science Institute, who specializes in interstellar object populations, explains the significance. The thick disk stars are like galactic senior citizens. They've seen the Milky Way evolve from a chaotic young galaxy full of star formation and mergers into the more sedate spiral we know today. An object coming from that population is carrying information about conditions that haven't existed for billions of years. The composition of 3I/Atlas provides additional age clues. Unlike younger comets that show signs of processing by cosmic radiation, 3I/Atlas appears remarkably pristine. This suggests that for most of its journey, it was large enough or active enough to protect its surface from the harsh environment of interstellar space. The fact that it still contains volatile ices like water and carbon monoxide after such an extended journey is actually quite surprising. It's like finding a perfectly preserved mammoth in permafrost, says Dr. Matthew Knight from the Naval Research Laboratory. The fact that 3I/Atlas still has pristine ice after potentially 7 billion years of cosmic radiation exposure tells us something remarkable about either its size, its composition, or its journey through space. The isotopic ratios, the relative amounts of different versions of the same elements, provide another age indicator. While we can't directly sample 3I/Atlas's composition, the spectroscopic analysis of its outgassing reveals isotope signatures that are consistent with formation in an ancient stellar environment with different chemical enrichment than our current galactic neighborhood. But perhaps the most profound implication of 3I/Atlas's age is what it represents for our understanding of galactic evolution. This isn't just a comet. It's a time capsule from an era when our galaxy was fundamentally different. Star formation rates were higher, stellar collisions were more common, and the chemical composition of interstellar space was simpler. When 3I/Atlas formed, explains Dr. Sarah Rugheimer from the University of Oxford, the galaxy had roughly half the heavy elements it has today. The conditions for planetary formation were different. The types of stars being born were different. In studying this object, we're literally examining a fossil from a different epoch of cosmic history. The preservation of such ancient material raises fascinating questions about the stability of interstellar space. How has 3I/Atlas survived close encounters with other stars? How many times has it been heated and cooled as it passed through different stellar systems? The fact that it's still shedding pristine water ice suggests its journey has been relatively gentle, avoiding the most violent regions of the galaxy. This cosmic archaeology extends beyond just 3I/Atlas itself. Every molecule of water vapor it releases, every grain of dust that sublimes from its surface, carries the chemical signature of its ancient origin. As Earth passes through the tail of material that 3I/Atlas leaves behind, our planet will literally be dusted with particles that predate our solar system by billions of years. The implications for astrobiology are staggering. If 3I/Atlas formed in a planetary system where life might have evolved, could it be carrying preserved organic compounds or even fossilized microorganisms from that ancient world? While the chances are vanishingly small, the possibility that we're being visited by a biological time capsule from the galaxy's youth is enough to make astrobiologists around the world take notice. Every interstellar visitor teaches us something new about the cosmos, reflects Dr. Ellen Howell from the University of Arizona. But 3I/Atlas is special. It's not just visiting us from another place. It's visiting us from another time. From the galactic thick disk to our backyard. To truly understand the magnitude of what 3I/Atlas represents, we need to embark on one of the most incredible journey stories ever told. A voyage that spans not just unimaginable distances, but virtually incomprehensible stretches of time. This isn't just a story about a comet traveling from another star system. This is the epic tale of a cosmic wanderer that has been homeless for longer than complex life has existed on Earth. Picture this: 7 billion years ago, when the universe was less than half its current age, our galaxy looked nothing like the elegant spiral we see today. The Milky Way was younger, more chaotic, filled with violent star formation and stellar collisions. In this ancient cosmic neighborhood called the galactic thick disk, stars burned hotter and died faster, and planetary systems formed under conditions we can barely imagine today. It was here, in this primordial stellar nursery, that 3I/Atlas was born. The galactic thick disk is like the galaxy's old neighborhood, the place where the first generation of metal-rich stars settled down and started forming planetary systems. These weren't the massive, short-lived stars that dominated the galaxy's earliest epochs, but middle-aged stars similar to our Sun, stable enough to nurture planetary systems for billions of years. Dr. Rosemary Wise from Johns Hopkins University, who studies galactic archaeology, paints the picture. The thick disk stars are the galaxy's memory keepers. They formed when the Milky Way was still settling into its current structure, when star formation rates were much higher and the chemical composition of space was fundamentally different. An object from this population is like finding a message in a bottle from the galaxy's youth. In some ancient planetary system within this thick disk region, probably orbiting a star not too different from our own Sun, 3I/Atlas began its existence as part of a larger body, perhaps an icy moon, a dwarf planet, or a massive comet in the outer reaches of its birth system. The conditions were perfect for preserving water, ice, and other volatiles. Temperatures never rose above -400 degrees Fahrenheit, and the cosmic environment was stable enough for complex ices to form and remain intact. But then, something catastrophic happened. Maybe it was a close encounter with a rogue planet, flung out of its own system by gravitational chaos. Perhaps a nearby star went supernova, disrupting planetary orbits across dozens of light years. Or it could have been something more subtle, the slow gravitational dance of stellar neighbors gradually perturbing the outer edges of the planetary system until objects like 3I/Atlas were nudged onto escape trajectories. Whatever the mechanism, 3I/Atlas found itself accelerated beyond its star's escape velocity, beginning a journey through the cosmic dark that would last longer than the entire history of complex life on Earth. The first million years of its journey would have been the most dramatic. As 3I/Atlas fled its birth system, it would have gradually cooled to the background temperature of space, just 2.7 Kelvin above absolute zero, or about -455 degrees Fahrenheit. Any remaining radioactive heating from its formation would have faded, leaving it as a frozen relic drifting through the void. But here's what makes 3I/Atlas's journey truly remarkable. For 7 billion years, it managed to avoid catastrophic encounters with other stars while somehow preserving its pristine ice composition. This tells us something incredible about the structure of our galaxy and the nature of interstellar space. The fact that 3I/Atlas survived this journey relatively intact is actually quite surprising, explains Dr. Ruth Murray Clay from UC Santa Barbara. Interstellar space isn't empty. It's filled with cosmic radiation, charged particles, and occasionally, objects pass close enough to other stars to be heated or disrupted. The preservation of volatile ices over such timescales suggests either remarkable luck or that interstellar space is more benign than we previously thought. Computer simulations of 3I/Atlas's possible journey paint a picture of cosmic billiards played on a galactic scale. Over 7 billion years, it would have encountered the gravitational influence of hundreds of stars, been accelerated and decelerated countless times, and potentially even made distant passes through other stellar systems. Each encounter would have subtly altered its trajectory, creating the complex orbital mechanics we observe today. The path from the galactic thick disk to our solar system isn't a straight line. Stars in our galaxy don't just sit still. They orbit the galactic center in complex patterns, rising and falling through the galactic plane like horses on a cosmic carousel. Our Sun, for example, completes one orbit around the galaxy every 230 million years, while simultaneously oscillating up and down through the galactic disk. 3I/Atlas's birth stars have completed roughly 30 galactic orbits since the object was ejected. The stellar neighborhood where it formed has been completely reshuffled by billions of years of galactic rotation. In fact, the stars that were 3I/Atlas's original neighbors are now scattered across thousands of light years, making it impossible to identify its specific birth system. But the most mind-bending aspect of 3I/Atlas's journey is the sheer scale of time involved. When this object began its interstellar wandering, Earth was a very different place. Our planet was still in its boring billion phase, a period when life consisted entirely of simple single-celled organisms floating in ancient oceans. There were no complex cells, no multicellular life, no oxygen in the atmosphere. The continents were barren rock under a methane-rich sky. Over the billions of years that 3I/Atlas drifted through space, life on Earth invented photosynthesis, filled the atmosphere with oxygen, evolved complex cells, developed multicellular organisms, survived multiple mass extinctions, saw the rise and fall of dinosaurs, witnessed the emergence of mammals, and eventually gave birth to human civilization. Our entire biological history, from the first DNA molecule to the invention of space telescopes, happened while 3I/Atlas was making its lonely journey between the stars. It's humbling to realize that this object has been traveling longer than complex life has existed on Earth, reflects Dr. Siegfried Egel from the University of Illinois. When 3I/Atlas began its journey, our planet was populated entirely by microbes. It's been wandering through space longer than it took for evolution to create everything from jellyfish to rocket scientists. The final act of this cosmic odyssey began roughly 50,000 years ago, when 3I/Atlas entered the outer gravitational influence of our Sun. Even at this distance, far beyond Pluto's orbit, our star's gravity began to bend the visitor's trajectory, setting up the hyperbolic approach we observe today. As it fell deeper into our solar system's gravitational well, 3I/Atlas began to accelerate, reaching speeds that would eventually peak at over 80 kilometers per second as it swings past the Sun in late 2025. But perhaps more importantly, for the first time in billions of years, the ancient ice began to feel the warmth of a star. The awakening was gradual at first. When 3I/Atlas crossed Neptune's orbit, solar heating was still negligible. But as it passed Uranus, then Saturn, the first wisps of water vapor began to escape its surface. By the time it reached Jupiter's distance from the Sun, the comet was developing a visible coma, announcing its presence to our increasingly sophisticated network of sky surveys. And that's how a 7 billion-year journey that began in the ancient galactic thick disk finally brought 3I/Atlas to humanity's attention on that historic night in July 2025. How AI and robots found what humans missed. The discovery of 3I/Atlas represents more than just finding another interstellar visitor. It marks a revolutionary moment in how we explore the cosmos. This wasn't found by a lone astronomer peering through a telescope or by accident during another observation. Instead, 3I/Atlas was discovered by an army of robots powered by artificial intelligence, representing the cutting edge of automated astronomical discovery. Welcome to the age of robotic astronomy, where machines scan the entire sky every single night, processing more data in an hour than human astronomers could analyze in a lifetime. The ATLAS system, which stands for Asteroid Terrestrial Impact Last Alert System, consists of 4 fully automated telescopes strategically positioned around the globe. 2 are located in Hawaii, 1 in Chile, and 1 in South Africa. Together, they form humanity's most advanced early warning system for potentially dangerous asteroids, but their capabilities extend far beyond planetary defense. Here's what makes ATLAS extraordinary. Every single night, weather permitting, these 4 telescopes automatically photograph the entire visible sky. Not just parts of it, not just interesting regions, the entire sky. Each telescope captures images covering 100 times the area of the full moon in a single shot, and they take these wide-field images every 60 seconds throughout the night. Dr. John Tonry from the University of Hawaii, the principal investigator for ATLAS, describes the scope. In a single night, ATLAS generates roughly 50,000 images containing over 500 million star and galaxy measurements. Over the course of a year, we're looking at the same patch of sky hundreds of times, creating a movie of the cosmos that shows everything that moves, brightens, dims, or appears. But here's the challenge. How do you find one potentially interesting object among 500 million data points every single night? This is where artificial intelligence enters the picture. The Atlas Discovery Pipeline employs sophisticated machine learning algorithms that have been trained on millions of known astronomical objects. These AI systems can distinguish between stars, galaxies, asteroids, comets, and various types of cosmic phenomena with accuracy that surpasses human astronomers. More importantly, they can do it in real time, processing each night's observations within hours of the data being collected. The AI system that spotted 3I/Atlas first noticed something unusual about object A11PL3Z, its preliminary designation, during the automated analysis of images taken on July 1, 2025. The object was moving against the background stars, which immediately flagged it as something within our solar system. But several features made the algorithms pause and flag it for priority follow-up. First, the trajectory was unusual. Most asteroids and comets follow predictable elliptical orbits around the Sun. Their motion across the sky follows patterns that astronomers have understood for centuries. But A11PL3Z was moving in a way that didn't fit any standard orbital model. Second, the object's brightness and color signature didn't match typical asteroid or comet characteristics. The spectral analysis, essentially the cosmic fingerprint revealed by breaking down the object's light into its component colors, showed features consistent with water ice and organic compounds, but with unusual ratios that didn't match any known solar system population. Most importantly, the preliminary orbit calculation suggested an eccentricity greater than 1.0, which would make it unbound to our Sun's gravity. This triggered automatic alerts to the Minor Planet Center and to observatories around the world. Dr. Richard Wainscoat, part of the Atlas team, explains the moment. Our AI flagged A11PL3Z as a high-priority target within 6 hours of discovery. The system essentially said, "I can't classify this object using any known category. Human experts need to look at this immediately." What followed was a beautiful example of human-AI collaboration. While the machines had detected something unusual, it took human expertise to understand what they had found. Astronomers at the University of Hawaii began detailed orbital analysis, while colleagues around the world pointed their telescopes at the object to gather additional observations. The confirmation process showcased the global nature of modern astronomy. The Catalina Sky Survey in Arizona provided crucial follow-up observations. The European Space Agency's Space Situational Awareness System tracked the object from Spain. Ground-based telescopes in Chile, Hawaii, and California all contributed precise position measurements. Within 24 hours, enough data had been collected to definitively confirm that this was indeed an interstellar visitor. But the technology behind this discovery goes even deeper than just the Atlas telescopes themselves. The entire system relies on advances in several cutting-edge fields. Advanced CCD sensors that can detect objects millions of times fainter than what the human eye can see. These sensors are so sensitive they can spot a candle flame on the moon. Real-time image processing algorithms that can compare each night sky to previous observations, identifying changes down to fractional pixel levels. The software essentially creates a difference image that highlights anything that has moved, appeared, or changed brightness. Machine learning classification systems trained on databases containing millions of known astronomical objects. These AI systems have learned to recognize the subtle differences between different types of cosmic phenomena, often outperforming human experts in speed and accuracy. Automated telescope control systems that can respond to discoveries within minutes, automatically pointing additional telescopes at interesting targets for follow-up observations. Global communication networks that instantly share discoveries with observatories worldwide, enabling rapid confirmation and detailed study of new objects. The discovery of 3I/Atlas also highlighted the crucial role of citizen science in modern astronomy. The Unistellar Network, consisting of over 15,000 amateur astronomers equipped with intelligent telescopes, was able to observe and track 3I/Atlas at magnitude 17.8, making it the faintest object ever detected by a citizen science network. What we're seeing is the democratization of astronomical discovery, says Dr. Frank Marchese from the SETI Institute, who helps coordinate the Unistellar Network. Amateur astronomers with relatively modest equipment can now contribute to cutting-edge research on interstellar visitors. This is citizen science on a scale we've never seen before. The success with 3I/Atlas has profound implications for the future of interstellar object discovery. The upcoming Vera C. Rubin Observatory, which achieved first light in 2025, will be even more powerful than Atlas. Its 8.4-meter telescope, equipped with a 3.2 gigapixel camera, will survey the entire southern sky every 3 nights, detecting objects down to magnitude 24, roughly 100 times fainter than what Atlas can see. Conservative estimates suggest the Rubin Observatory will discover dozens to hundreds of interstellar visitors during its 10-year survey. We're transitioning from a world where interstellar objects are rare, lucky discoveries to one where they become routine detections, enabling statistical studies of interstellar populations for the first time in human history. The discovery of 3I/Atlas represents a turning point, explains Dr. Mario Jurek from the University of Washington, who leads the Rubin Observatory's data management team. We're moving from an era of individual discoveries to an era of population studies. Instead of analyzing 3 interstellar visitors, we'll soon be analyzing hundreds, revealing patterns and properties we can't even imagine yet. We've seen this before. Meet Oumuamua. Before we can fully appreciate the significance of 3I/Atlas, we need to travel back to October 19, 2017, the day that changed everything we thought we knew about visitors from other star systems. This was the day humanity got its first confirmed glimpse of an object that originated beyond our solar system, and it was nothing like what anyone expected. Dr. Robert Warwick was doing what he did every morning at the University of Hawaii's Institute for Astronomy, scanning through the previous night's data from the Pan-STARRS-1 telescope. Pan-STARRS, which stands for Panoramic Survey Telescope and Rapid Response System, was designed to hunt for potentially dangerous asteroids, but on this particular morning, it had captured something far more extraordinary. I was looking through the nightly data when I noticed this very faint object moving unusually fast, Warwick later recalled. At first, I thought it might be space junk or a measurement error. Objects in our solar system just don't move like this thing was moving. The object, initially designated C/2017U1, appeared as nothing more than a tiny point of light crawling across the star field. But when Warwick calculated its preliminary orbit, the numbers made his coffee go cold. The eccentricity was 1.2, meaning this object was moving too fast to be captured by the sun's gravity. It was just passing through. Within days, observatories around the world were tracking this mysterious visitor. The European Southern Observatory's Very Large Telescope in Chile captured detailed images. The Gemini Observatory in Hawaii measured its brightness variations. The Discovery Channel Telescope in Arizona tracked its changing position against the stars. And then came the first shock. This thing was spinning like a tumbling football, completing one rotation every 7.3 hours. But more shocking still was what this tumbling revealed about its shape. As 1I/Oumuamua rotated, its brightness varied by a factor of 10, meaning it was at least 10 times longer than it was wide. In 3-dimensional terms, it was roughly 400 meters long, 40 meters wide, and 40 meters thick. It was like nothing we'd ever seen, says Dr. Alan Fitzsimmons from Queen's University Belfast, who led some of the early observational campaigns. Imagine a cosmic cigar or perhaps a giant space cucumber tumbling end over end. The extreme elongation was completely unprecedented for any natural object in our solar system. The color was equally puzzling. Oumuamua appeared dark red, similar to objects in the outer regions of our solar system that have been weathered by billions of years of cosmic radiation. But this raised immediate questions. If it came from interstellar space, why did it look like objects that had spent eons in our solar system? Then came the second shock, discovered through painstaking analysis of Hubble Space Telescope observations. Oumuamua was accelerating away from the sun in a way that couldn't be explained by gravity alone. It was experiencing a tiny but measurable push that was gradually changing its trajectory. Dr. Marco Micheli from the European Space Agency's Space Situational Awareness Program was part of the team that first detected this non-gravitational acceleration. When we saw the deviation from a purely gravitational trajectory, we knew we were dealing with something truly extraordinary. The acceleration was tiny, about 5 millimeters per second squared, but it was real and it was consistent. This discovery triggered intense scientific debate. Comets routinely experience non-gravitational forces when they heat up and outgas material, creating a rocket-like effect. But Oumuamua showed no signs of the typical comet behavior: no coma, no tail, no detectable water vapor or dust emission. It looked like an asteroid but was behaving like a comet. The mystery deepened when astronomers tried to determine what Oumuamua was made of. Spectroscopic analysis revealed a surface that appeared dry and rocky, with no signs of water, ice, or other volatiles that typically drive cometary activity. Yet something was causing that acceleration. We had an object that looked like an asteroid, had the composition of an asteroid, but was accelerating like a comet without showing any cometary activity, explains Dr. Davide Farnochia from NASA's Jet Propulsion Laboratory. It was like encountering an animal that looked like a fish, lived in water like a fish, but could fly like a bird. The scientific community proposed various explanations. Maybe Oumuamua was experiencing radiation pressure from sunlight reflecting off its surface. Perhaps it was a very unusual type of comet that outgassed material too faint to detect. Some suggested it might be a fragment of a larger object that had been disrupted by tidal forces. But the most sensational theory came from Dr. Avi Loeb, a respected astrophysicist at Harvard University. In a series of papers and public statements, Loeb suggested that Oumuamua's extreme shape and unusual acceleration could be explained if it were artificial, a piece of alien technology, perhaps a light sail or probe from another civilization. The possibility that this is artificial doesn't mean it's likely, Loeb carefully explained. But the scientific method requires us to consider all possibilities, including ones that might seem exotic. Oumuamua had properties unlike any natural object we've encountered, so we should at least consider whether it might be artificial. The alien hypothesis sparked enormous public interest and heated scientific debate. The search for extraterrestrial intelligence, SETI, Institute pointed radio telescopes at Oumuamua, listening for any signals that might indicate artificial origin. They found none. Other astronomers pointed out that there were natural explanations for all of Oumuamua's strange properties, even if those explanations were themselves quite exotic. The mystery seemed destined to remain unsolved as Oumuamua rapidly faded from view, racing away from the sun at over 40 kilometers per second. By January 2018, it had become too faint for even the most powerful telescopes to observe, taking its secrets with it into the cosmic dark. But science has a way of solving mysteries, even when the primary evidence has disappeared. In 2023, a breakthrough came from an unexpected source: laboratory studies of how cosmic radiation affects ice in space environments. Dr. Jennifer Bergner from UC Berkeley and Dr. Daryl Seligman from Cornell University published a landmark study that finally solved the Oumuamua puzzle. They demonstrated that cosmic ray radiation can penetrate into solid ice and create hydrogen gas trapped within the crystal structure. When an icy object approaches a star and heats up, this trapped hydrogen can outgas without creating a visible coma or tail. The hydrogen outgassing model explains everything we observed about Oumuamua, Bergner explains. The acceleration magnitude, the direction, the timing, it all fits perfectly with an object that contains hydrogen-rich ice but doesn't show typical cometary activity because hydrogen is invisible to our telescopes. This breakthrough was supported by the discovery of similar objects within our own solar system. Astronomers identified more than a dozen dark comets, objects that appear asteroid-like but show small non-gravitational accelerations consistent with hydrogen outgassing. Oumuamua, it turns out, represents a class of objects that exists throughout the galaxy. Finding Oumuamua was like discovering a new species of animal, reflects Dr. Matthew Knight from the Naval Research Laboratory. At first, it seemed completely unique and inexplicable. But as we learned more about cometary physics and found similar objects in our own solar system, we realized we'd encountered the first member of a previously unknown population of interstellar visitors. The legacy of Oumuamua extends far beyond just solving its individual mysteries. It proved that interstellar objects regularly visit our solar system, validating decades of theoretical predictions. It demonstrated that these visitors could have properties unlike anything in our local cosmic neighborhood. Most importantly, it prepared the astronomical community for future discoveries by establishing observational protocols and international cooperation frameworks. Oumuamua also highlighted the limitations of our current detection capabilities. Despite being the largest interstellar object we discovered at the time, it was only detected after it had already passed its closest approach to the Sun and was heading back toward interstellar space. We missed the opportunity to study it during its most active phase, when heating from our Sun might have revealed more about its composition and internal structure. Oumuamua taught us that we need to be watching the sky constantly and be ready to respond quickly when we find these visitors, says Dr. Lindley Johnson from NASA's Planetary Defense Coordination Office. Every interstellar object is a unique scientific opportunity that we can't afford to miss. The name Oumuamua itself reflects the cultural significance of this discovery. Chosen by the International Astronomical Union from a suggestion by the Pan-STARRS team, it's a Hawaiian word meaning a messenger from afar arriving first, a fitting description for humanity's first confirmed interstellar visitor. As telescopes around the world continue to search for more interstellar visitors, Oumuamua remains the benchmark against which all future discoveries are compared. It opened the door to a new field of astronomy and changed our understanding of how common material exchange might be between stellar systems throughout the galaxy. Borisov, the normal interstellar comet. Just 2 years after Oumuamua baffled astronomers with its mysterious properties, the cosmic universe delivered a follow-up act that was both more conventional and, in its own way, equally remarkable. On August 30th, 2019, amateur astronomer Gennady Borisov was doing what he had done nearly every clear night for years, scanning the sky from his backyard observatory in Nakhnij, Crimea, using a telescope he had built himself. Borisov wasn't affiliated with any major research institution. He wasn't part of an international asteroid survey program. He was simply a passionate amateur astronomer who had been searching for comets for over a decade, driven by the pure love of discovery. On this particular night, that passion was about to make history. I was taking my usual survey images when I noticed a fuzzy object that wasn't in the same position as the previous night, Borisov later explained through an interpreter. At first, I thought it might be a known comet, but when I checked the databases, there was nothing listed in that location. What Borisov had discovered using a 0.65-meter telescope in his backyard was an object that would soon be designated 2I/Borisov, the second confirmed interstellar visitor to our solar system. But unlike the mysterious and confounding Oumuamua, this new visitor looked and behaved exactly like what astronomers expected an interstellar comet should look like. The confirmation process was swift and efficient, benefiting from the protocols established during the Oumuamua discovery. Within 24 hours, observatories around the world were tracking the object. The preliminary orbit calculations quickly showed an eccentricity of around 3.4, unambiguously hyperbolic and proving beyond doubt that this object originated from outside our solar system. But what made 2I/Borisov special wasn't just that it was interstellar, it was that it looked perfectly normal. As it approached the Sun, it developed a beautiful, classic cometary coma and tail. Spectroscopic analysis revealed water vapor, dust, and other compounds typical of comets from our own solar system. Here, finally, was an interstellar visitor that behaved the way theory predicted such objects should behave. After the puzzling nature of Oumuamua, finding Borisov was almost a relief, admits Dr. Chuanji Yi from the University of Maryland, who led several observational campaigns. It looked like a comet, acted like a comet, and had the composition of a comet. In many ways, it was the interstellar visitor we expected to find first. The nucleus of 2I/Borisov was estimated to be roughly 975 meters long, larger than Oumuamua, but within the normal size range for comets in our solar system. As it heated up during its approach to the Sun, it began shedding material at a prodigious rate, losing roughly 2 to 4 kilograms of dust per second and about 60 kilograms of water per second at peak activity. But while 2I/Borisov looked normal on the surface, detailed analysis revealed it was carrying remarkable secrets about its ancient origin. The key breakthrough came from spectroscopic studies that measured the relative abundances of different molecules in its coma. Dr. Martin Cordner from NASA's Goddard Space Flight Center led one of the most significant studies, using the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile to measure carbon monoxide in Borisov's coma. What they found was extraordinary. The carbon monoxide to water ratio was between 55% and 105%, meaning Borisov contained nearly as much carbon monoxide as water ice. That result was stunning, Cordner explains. Comets in our solar system typically have carbon monoxide to water ratios of only 0.5% to 4%. Borisov's composition was completely off the charts, indicating it formed under very different conditions than anything in our local cosmic neighborhood. This extreme carbon monoxide abundance told a fascinating story about Borisov's birth environment. Carbon monoxide only remains stable in solid form at extremely low temperatures, below about minus 420 degrees Fahrenheit, minus 250 degrees Celsius. For Borisov to retain such high concentrations, it must have formed in the very cold outer regions of its birth system, probably around a star much cooler and dimmer than our Sun. The most likely scenario places Borisov's origin around an M-dwarf star, a small, cool red star that represents about 75% of all stars in our galaxy. These stars burn so dimly that their habitable zones are much closer in, but their outer planetary systems remain extremely cold, creating perfect conditions for carbon monoxide-rich comets like Borisov. Borisov is essentially a refrigerated sample from another star system, says Dr. Stefano Bagnolo from the Armagh Observatory and Planetarium. Its composition provides direct evidence about conditions in the outer regions of a planetary system that formed around a very different type of star than our Sun. Additional studies revealed even more remarkable properties. Polarimetric observations, which measure how light is scattered by dust particles in the coma, showed that Borisov's dust was remarkably homogeneous across its entire coma. This uniformity extended over distances of more than 20,000 kilometers, suggesting the comet's material was completely pristine and unaltered by its journey through interstellar space. Dr. Ludmila Kolokolova from the University of Maryland, who led the polarimetric studies, emphasizes the significance. The level of homogeneity we observed in Borisov is unprecedented. It suggests this object has been essentially unchanged since it formed in its birth system, possibly billions of years ago. We're seeing a completely uncontaminated sample of materials from another world. Unlike Oumuamua, which was discovered too late for optimal observation, Borisov was found while it was still approaching the Sun, providing astronomers with months of observation time. This extended observation period allowed for unprecedented detailed study of an interstellar visitor. The European Space Agency's Hubble Space Telescope captured dramatic images showing Borisov's nucleus fragmenting in March 2020, shedding material in what appeared to be a natural outgassing event rather than a catastrophic breakup. These observations provided insights into the internal structure and composition of interstellar comets. Watching Borisov fragment was like getting a cross-section view of an interstellar object, explains Dr. David Jewett from UCLA, who led the Hubble observations. We could see how the material was distributed within the nucleus and watch how different layers responded to solar heating. It was an unprecedented opportunity to study the internal structure of a visitor from another star system. The discovery also highlighted the crucial role of amateur astronomers in modern astronomy. Gennady Borisov's find demonstrated that some of the most significant discoveries in astronomy can still come from dedicated individuals working with relatively modest equipment, rather than large institutional survey programs. Borisov's discovery reminds us that astronomy is still a field where passionate individuals can make world-changing discoveries, reflects Dr. Gareth Williams from the Minor Planet Center. Professional surveys are finding more objects than ever before, but there's still room for the dedicated amateur who knows the sky intimately and has the persistence to keep looking night after night. The legacy of 2I/Borisov extends beyond its individual characteristics to what it taught us about the population of interstellar objects. By providing a normal example of an interstellar comet, it helped establish baseline expectations for future discoveries and demonstrated that interstellar visitors could indeed carry pristine samples from their birth environments. Perhaps most importantly, Borisov proved that interstellar objects aren't just rare curiosities. They're regular visitors that can provide direct information about planetary formation processes around other types of stars. Its extreme carbon monoxide content revealed that planetary systems around M-dwarf stars can produce objects with compositions completely unlike anything in our solar system. Borisov was our first clear window into the composition of planetary materials around other stars. Summarizes Dr. Alan Stern from the Southwest Research Institute. It showed us that the diversity of planetary system chemistry is much greater than we had imagined, and that interstellar visitors can serve as natural space probes carrying samples from distant worlds. The success of the Borisov observational campaign also established protocols and international cooperation frameworks that would prove crucial for studying future interstellar visitors like 3I/Atlas. The lessons learned from tracking and analyzing Borisov created a template for rapid response to these fleeting cosmic opportunities. 3 visitors, 3 stories. Now that we've met all 3 members of humanity's first confirmed interstellar family, it's time to step back and see what their collective story tells us about the cosmos beyond our solar system. Oumuamua, Borisov, and 3I/Atlas aren't just individual curiosities. They're representatives of vast populations of objects wandering between the stars, each carrying unique information about the diversity of planetary systems throughout our galaxy. What's immediately striking is just how different these 3 visitors are from each other. If you were to encounter them without knowing their interstellar origin, you might think they came from completely different types of cosmic environments. And in fact, that's exactly what they represent. Oumuamua, the mysterious minimalist. Oumuamua remains the most enigmatic of our 3 visitors, a cosmic messenger that arrived with more questions than answers. Its extreme 10:1 elongated shape is unlike anything we've found in our solar system. Its dark reddish color suggests either significant age or specific formation conditions. Most puzzling of all, it showed the behavior of a comet non-gravitational acceleration, without any of the visible signs we associate with cometary activity. The 2023 breakthrough identifying hydrogen outgassing as the source of Oumuamua's acceleration finally provided a natural explanation for its behavior, but it also revealed something profound about interstellar space. Objects can spend millions or billions of years in the cosmic deep while still retaining enough volatile material to become active when they encounter a star. Oumuamua taught us that our assumptions about what interstellar objects should look like were completely wrong. Reflects Dr. Michelle Bannister from the University of Canterbury. We expected interstellar visitors to be either obviously cometary or obviously rocky. We didn't anticipate objects that could hide their true nature so effectively. Oumuamua likely represents objects from the inner regions of planetary systems, rocky or icy bodies that were ejected during the chaotic early phases of planetary formation. Its composition and properties suggest it formed closer to its parent star, where conditions were warmer and hydrogen-rich ices could form and be preserved. Borisov, the textbook comet. In complete contrast, 2I/Borisov appeared to be exactly what theory predicted an interstellar comet should look like. It had a visible coma and tail, showed clear water vapor emission, and behaved in every way like a classical comet. But its normal appearance masked a revolutionary discovery about planetary chemistry around other stars. The extreme carbon monoxide abundance in Borisov, up to 105% relative to water, revealed conditions completely unlike anything in our solar system. This composition points to formation in the extremely cold outer regions of a planetary system, probably around a dim M-dwarf star where temperatures never rose above -420 degrees Fahrenheit. Borisov is a refrigerated sample from the outer reaches of an alien planetary system, explains Dr. Martin Cordiner. Its composition tells us that planetary formation around small, cool stars produces objects with chemistry that's radically different from our own solar system. Borisov represents the population of objects from the cold outer regions of planetary systems, true iceball comets that formed in environments so cold that carbon monoxide could remain stable for billions of years. Its pristine composition suggests it was ejected relatively gently from its birth system, avoiding the violent processes that might have altered its chemistry. 3I/Atlas, the ancient wanderer. 3I/Atlas brings yet another completely different perspective to our interstellar family. Potentially 7 billion years old, it represents objects from the galaxy's ancient past, materials that formed when our Milky Way was less than half its current age and had very different chemical composition and stellar populations. Unlike Oumuamua's minimal activity or Borisov's conventional cometary behavior, 3I/Atlas shows vigorous water-dominated outgassing with clear dust production. Its record-breaking orbital eccentricity of 6.141 indicates it has been wandering through interstellar space for billions of years, potentially visiting multiple stellar systems during its cosmic odyssey. 3I/Atlas is a time capsule from the galaxy's youth, says Dr. Amaya Morrow-Martin. It's carrying information about conditions that existed when the first generation of heavy element-rich stars were forming planetary systems. We're literally touching materials that predate our solar system by billions of years. The large size of 3I/Atlas, potentially 1 to 11 kilometers across, also sets it apart from its smaller predecessors. This suggests that large objects can survive billions of years of interstellar travel, gradually losing material through sublimation and impacts but retaining enough mass to remain active when they encounter a new star. The bigger picture, what 3 visitors tell us. Collectively, these 3 objects reveal that interstellar space is filled with a diverse population of visitors carrying samples from many different types of planetary systems and stellar environments. They represent different formation zones, inner versus outer planetary systems, different stellar types, Sun-like versus M-dwarf stars, and different epochs of galactic evolution, contemporary versus ancient thick disk. The diversity is actually more remarkable than if all 3 objects had been similar. It suggests that planetary systems throughout the galaxy produce and eject objects through many different mechanisms, creating a vast population of interstellar wanderers with a wide range of properties and origins. The fact that our first 3 interstellar visitors are so different from each other is actually the most important discovery, emphasizes Dr. Alan Fitzsimmons. It means the galaxy is full of objects carrying samples from every possible type of planetary environment. We're not just seeing rare exceptions. We're glimpsing a vast, diverse population that we're only beginning to understand. The objects also demonstrate different preservation mechanisms for surviving billion-year journeys through interstellar space. Oumuamua preserved hydrogen-rich ice through unknown mechanisms. Borisov maintained pristine carbon monoxide through extremely cold formation conditions. 3I/Atlas retained water ice and organics possibly through its large size and protective outgassing. Implications for astrobiology. From an astrobiological perspective, our 3 visitors represent different pathways for distributing organic compounds and possibly even life itself throughout the galaxy. All 3 show evidence of complex chemistry that could include the building blocks of life. Oumuamua's hydrogen-rich composition suggests water chemistry that could support biological processes. Borisov's carbon monoxide abundance indicates carbon chemistry under extreme conditions that might produce unique organic compounds. 3I/Atlas's ancient origins and current water activity suggest it could be carrying organic compounds that formed under very different galactic conditions billions of years ago. Each interstellar visitor represents a different pathway for spreading life's building blocks throughout the galaxy, explains Dr. Lucas Paganini from NASA Goddard. If panspermia, the distribution of life between worlds, occurs on galactic scales, these objects would be the carriers. The detection revolution. Perhaps most importantly, the progression from Oumuamua, discovered after closest approach, to Borisov, discovered approaching, to 3I/Atlas, discovered well before perihelion, demonstrates our rapidly improving ability to detect and study these cosmic messengers. The upcoming Vera C. Rubin Observatory will likely discover dozens to hundreds of interstellar visitors, transitioning us from studying individual objects to analyzing statistical populations. This will enable us to understand not just the properties of specific visitors, but the overall demographics of interstellar object populations throughout our galaxy. We're moving from a world where interstellar objects are rare, lucky discoveries to one where they become routine detections, predicts Dr. Mario Jurek from the University of Washington. The real revolution will come when we have enough objects to do population studies, understanding not just individual visitors, but the entire ecosystem of materials flowing between star systems. The 3 confirmed interstellar visitors have opened a new window into galactic dynamics, planetary formation, and the cosmic distribution of complex chemistry. They've proven that our solar system regularly receives messages from distant worlds, written in ice and rock and delivered across vast stretches of space and time. Most remarkably, They've shown us that we're finally developing the technology to read these ancient cosmic letters and understand what they're telling us about our place in the galaxy. The hidden truth. We're surrounded by alien objects. Here's a mind-bending truth that will change how you think about our place in the cosmos. Right now, as you're watching this, there are thousands of objects from other star systems silently drifting through our solar system. Not 3, not dozens, thousands. The discovery of Oumuamua, Borisov, and 3I/Atlas isn't just about finding 3 rare cosmic visitors. It's about discovering that we live in a galactic neighborhood where interstellar objects are actually commonplace. This revelation completely overturns what astronomers believed just a decade ago. Before 2017, interstellar objects were purely theoretical, things that should exist according to computer models but had never been directly observed. The conventional wisdom was that such visitors would be incredibly rare, perhaps 1 detected per decade if we were lucky. But the rapid discovery of 3 interstellar objects in just 8 years suggests something completely different. We're not witnessing rare exceptions, but rather the tip of an enormous iceberg. Dr. Abraham Loeb from Harvard University, despite his controversial theories about Oumuamua, made a crucial calculation that shocked the astronomical community. Based on the discovery rate and our detection capabilities, there should be roughly 10,000 Oumuamua-sized objects within Neptune's orbit at any given time. 10,000 visitors from other star systems, just sitting there, most of them too small and distant for us to detect. Let that sink in for a moment. 10,000 objects from alien worlds, drifting through the space between our planets right now. Some are probably closer to you than the moon. Others are lurking beyond Pluto, temporarily captured in loose orbits around our sun. A few might be on collision courses with planets, potentially delivering interstellar material to worlds throughout our solar system. But the numbers get even more staggering when you consider smaller objects. Dr. Gregory Laughlin from UC Santa Cruz extended these calculations to objects the size of basketballs or cars. If we could detect objects down to a meter in diameter, we'd probably find millions of interstellar visitors in our solar system at any given time. Our solar system is essentially swimming in a sea of materials from other worlds. This hidden population explains why our first detected interstellar objects were so different from each other. We're not seeing representatives of one specific type of interstellar visitor. We're sampling from a vast, diverse population that includes objects from every conceivable type of planetary system and stellar environment. Think of it like this. Imagine you're trying to understand Earth's wildlife by randomly catching 3 animals. You might catch a penguin, a cactus, and a whale. From this sample, you'd correctly conclude that Earth has incredible biological diversity, but you'd have no idea about the millions of other species you hadn't encountered yet. That's exactly where we are with interstellar objects. The detection challenge. So why are we only now discovering these cosmic neighbors? The answer reveals just how vast and dark space really is, and how primitive our detection capabilities have been until very recently. Most interstellar objects are small, probably ranging from boulder-sized chunks to kilometer-scale bodies like 3I/Atlas. They're also incredibly dark, typically reflecting only 3 to 5% of the sunlight that hits them. This makes them roughly as dark as charcoal, and they're moving against the already dark background of space. Dr. Robert Warwick, who discovered Oumuamua, puts the challenge in perspective. Finding an interstellar object is like trying to spot a piece of charcoal tumbling past a streetlight while you're standing several miles away, and the charcoal is moving faster than a speeding bullet. Oh, and you only get to look for a few hours each night, and clouds might block your view. The situation is made even more difficult by the trajectories these objects follow. Unlike comets from our solar system that follow predictable elliptical orbits and return periodically, interstellar visitors are just passing through. They appear from nowhere, zip through our solar system in a matter of months, and then disappear forever into interstellar space. This means we have only a brief window to detect them, usually when they're relatively close to the sun and reflecting enough light to be visible. Miss that window, and the object vanishes into the cosmic dark, never to be seen again. The revolution in sky surveys. The reason we're suddenly finding interstellar objects isn't because they're becoming more common. It's because our ability to search for them has undergone a revolution. The transition from photographic plates to digital cameras the development of automated survey telescopes, and the application of artificial intelligence to astronomical data processing have transformed our cosmic surveillance capabilities. The Catalina Sky Survey, Pan-STARRS, Atlas, and now the Vera-C Rubin Observatory represent a new generation of robotic sentries that scan the entire visible sky nightly. These systems can detect objects millions of times fainter than what the human eye can see, and they can spot movement against the stellar background down to tiny fractions of a pixel. We've gone from occasionally stumbling across asteroids to systematically cataloging everything that moves in the solar system, explains Dr. Lindley Johnson from NASA's Planetary Defense Coordination Office. In the process, we've discovered that our solar system is far more crowded with visitors than anyone imagined. The Vera-C Rubin Observatory, which achieved first light in 2025, represents the next quantum leap in detection capability. Its 8.4-meter telescope equipped with a 3.2 gigapixel camera will survey the entire southern sky every 3 nights, detecting objects down to magnitude 24, roughly 100 times fainter than current surveys can spot. Conservative estimates suggest Rubin will discover 1 to 3 Oumuamua-sized interstellar objects per year. More optimistic projections suggest dozens annually. But perhaps most exciting are the predictions for smaller objects. Rubin might detect hundreds or even thousands of meter-sized interstellar visitors, finally giving us a statistical sample large enough to understand the true demographics of our galactic neighborhood. The frequency revolution. Recent studies have revised upward the estimates of how often interstellar objects visit our solar system. Dr. David Trilling from the University of Arizona led a comprehensive analysis combining discovery rates with detection efficiency models. Based on our current data, roughly 7 objects larger than 100 meters in diameter pass within Earth's orbit every year. That means every few months, something the size of a city block cruises through the inner solar system. But it gets even more frequent for smaller objects. Objects the size of houses probably pass through weekly. Car-sized interstellar visitors might zip past daily. And basketball-sized chunks from other worlds could be passing by every few hours. This frequency has profound implications for understanding material exchange between stellar systems. Our solar system isn't isolated. It's constantly receiving samples from throughout the galaxy. Over billions of years, we've probably been visited by materials from millions of different planetary systems. Earth is essentially being dusted with interstellar material on a regular basis, says Dr. Phil Bland from Curtin University, who studies cosmic dust and meteorites. Most of it burns up in our atmosphere as meteors, but some fraction survives and lands on our surface. We might literally be walking on particles from other worlds every day. The Discovery Pipeline. Understanding the true abundance of interstellar visitors requires grappling with selection effects, the biases in what we're able to detect versus what's actually out there. Current surveys are most sensitive to objects that come relatively close to the sun and have moderate to large sizes. We're blind to most small objects, anything that stays in the outer solar system, and visitors that approach from directions we're not monitoring. Dr. Matthew Holman from the Harvard-Smithsonian Center for Astrophysics has modeled these detection biases extensively. For every interstellar object we detect, there are probably 100 others that pass through unnoticed. Our current surveys are like having a few fishing nets scattered across the Pacific Ocean. We'll catch some fish, but most of the marine life swims by undetected. This means the true population of interstellar visitors is likely far larger than even our revised estimates suggest. We're still in the very early stages of understanding how much cosmic material flows between star systems and how often our solar system receives these ancient messengers. Implications for planetary defense. The recognition that interstellar objects are common has also raised new questions for planetary defense efforts. While the vast majority of these visitors pose no threat to Earth, the possibility of a dangerous impact can't be completely dismissed. Interstellar objects approach from random directions at very high speeds, often 2 to 3 times faster than typical solar system asteroids. This means we'd have less warning time if one were on a collision course with Earth, and deflection missions would be more challenging due to the high approach velocities. We're not losing sleep over interstellar impactors, clarifies Dr. Kelly Fast from NASA's Planetary Defense Office. The probability is extremely low, and most interstellar objects are small enough that they'd burn up in our atmosphere anyway. But it's another factor we need to consider in our overall planetary defense strategy: the cosmic perspective. Perhaps the most profound implication of discovering we're surrounded by interstellar visitors is what it tells us about our cosmic context. Our solar system isn't an isolated island in space. It's part of a vast galactic ecosystem where materials, and possibly even life itself, flow freely between stellar systems. Every star system in our galaxy is probably experiencing the same phenomenon. Right now, chunks of rock and ice that originated in our solar system are drifting through alien star systems, carrying samples of Earth's neighborhood to worlds we can barely imagine. The realization that interstellar objects are common means that planetary systems throughout the galaxy are all connected, reflects Dr. Alan Stern from the Southwest Research Institute. We're part of a galactic community where materials, and possibly biology, are constantly being exchanged. It's a much more interconnected universe than we ever imagined. This cosmic perspective transforms how we think about the search for life beyond Earth. If organic compounds and even microorganisms can survive the journey between star systems aboard interstellar objects, then life itself might be a galactic phenomenon rather than something that develops independently on isolated worlds. The hidden truth is that we live in a universe far more dynamic and interconnected than previous generations could have imagined. The space around us isn't empty. It's filled with messages from distant worlds, written in rock and ice and delivered across vast stretches of space and time. We're finally developing the technology to read these messages and understand what they're telling us about our place in the cosmic community. What 3I/Atlas tells us about other solar systems. 3I/Atlas isn't just a cosmic curiosity. It's a natural space probe that has delivered direct samples from an alien planetary system to our doorstep. Every molecule of water vapor streaming from its surface, every grain of dust in its coma, carries encoded information about conditions that existed in another star system billions of years ago. In studying 3I/Atlas, we're essentially doing planetary science on a world we'll never visit, around a star we may never identify. This represents a completely new way of exploring the cosmos. Instead of trying to detect the faint light of distant exoplanets or inferring their properties from subtle gravitational effects, we can literally hold pieces of other worlds in our hands and analyze them in Earth-based laboratories. Decoding the chemical fingerprint. The spectroscopic analysis of 3I/Atlas reveals a chemical story that spans billions of years and countless light years. Unlike terrestrial rocks that have been processed and reprocessed by geological activity, or even meteorites from our solar system that show signs of thermal alteration, 3I/Atlas carries pristine materials that have been preserved in cosmic deep freeze since its formation. Dr. Lucas Paganini from NASA Goddard Space Flight Center, who leads spectroscopic studies of interstellar visitors, explains the significance. When we analyze the light coming from 3I/Atlas's coma, we're seeing the direct chemical signature of materials that formed around another star. It's like finding an uncontaminated archaeological artifact from an alien civilization, except instead of pottery shards, we're examining the actual building blocks that went into making another planetary system. The water ice in 3I/Atlas provides crucial insights into the temperature and chemical conditions of its birth environment. Water ice forms through specific processes that depend on temperature, pressure, and the availability of hydrogen and oxygen. The isotopic ratios of hydrogen and oxygen in 3I/Atlas's water, essentially the relative amounts of heavy and light versions of these elements, act like a cosmic thermometer, revealing the temperature conditions where this ice originally formed. Preliminary analysis suggests the water in 3I/Atlas has isotopic signatures consistent with formation in the outer regions of a planetary system, where temperatures remain below -350 degrees Fahrenheit for billions of years. This is similar to conditions in the outer reaches of our own solar system, but the subtle differences in isotopic ratios indicate it formed around a star with slightly different composition than our Sun. The dust tells a story. Perhaps even more revealing than the water vapor is the dust streaming from 3I/Atlas's surface. This dust consists of tiny solid particles, some no larger than smoke particles, others as big as grains of sand, that represent the rocky and organic building blocks of its birth world. Dr. John Paolo Tozzi from the Arce Tri Astrophysical Observatory has been analyzing the color and scattering properties of this dust using advanced polarimetric techniques. The dust from 3I/Atlas has a very specific signature that tells us about the chemical composition and formation processes in its original environment. We can determine what minerals are present, how they formed, and even estimate the radiation environment where they originated. The dust particles reveal evidence of complex organic compounds, carbon-based molecules that could include some of the chemical building blocks of life. While the specific identification of these compounds requires more detailed analysis, their presence suggests that the planetary system where 3I/Atlas originated was capable of producing complex carbon chemistry. Finding organic compounds in interstellar visitors like 3I/Atlas proves that the chemistry of life isn't unique to Earth, says Dr. Jamie Elsela from NASA Goddard. The same types of carbon-based molecules that are essential for biology on our planet can form around other stars and survive billion-year journeys through interstellar space. Reading the formation environment. The size, activity level, and preservation state of 3I/Atlas provide clues about the type of planetary system where it originated. Its large size, potentially up to 11 kilometers across, suggests it formed in a system where icy bodies could grow to substantial sizes without being disrupted by gravitational perturbations. This points to a planetary system that was relatively stable during its early formation phases. Unlike chaotic systems where gravitational interactions would have shattered large icy bodies, 3I/Atlas's birth system allowed objects to accrete and maintain their integrity over billions of years. Dr. Alessandro Morbidelli from the Observatoire de la Côte d'Azur, who studies planetary formation dynamics, offers his interpretation. The fact that 3I/Atlas survived as a large, coherent object for billions of years tells us something important about its birth environment. It probably formed in the outer regions of a relatively calm planetary system, perhaps around a star that didn't experience the violent early evolution that characterizes some stellar types. The preservation of volatile ices like water and potential carbon monoxide also reveals information about the radiation environment in its birth system. High-energy stellar radiation and cosmic rays can break down these delicate compounds over time. The fact that 3I/Atlas still contains abundant volatiles suggests either that it formed around a relatively quiet star or that it was large enough to protect its interior from radiation damage. Stellar archaeology through isotopes. One of the most powerful techniques for understanding 3I/Atlas's origin involves studying isotopic ratios, the relative abundances of different versions of the same chemical elements. These ratios act like cosmic DNA, encoding information about the stellar environment where the elements originally formed. Different types of stars produce elements through different nuclear processes, and these processes leave distinctive isotopic signatures. By measuring the ratios of isotopes like carbon-12 to carbon-13 or oxygen-16 to oxygen-18 in 3I/Atlas's outgassing material, astronomers can potentially identify what type of star it originated around. Dr. Cannell Alexander from the Carnegie Institution for Science, who specializes in isotopic analysis of extraterrestrial materials, explains the detective work. Isotopic ratios are like stellar fingerprints. If we can measure them precisely enough in 3I/Atlas, we might be able to determine whether it came from around a sun-like star, a more massive star, or perhaps a star that formed in a different part of the galaxy with different chemical enrichment. Early measurements suggest isotopic signatures that are broadly similar to materials in our solar system, indicating that 3I/Atlas likely originated around a star with comparable mass and composition to our Sun. However, subtle differences hint at formation in a stellar environment that was slightly enriched in heavy elements compared to our local galactic neighborhood. Age and galactic evolution. The estimated 7 billion year age of 3I/Atlas makes it a unique window into conditions during an earlier epoch of galactic evolution. When this object formed, our galaxy had roughly half the heavy elements it contains today. Star formation rates were higher, and the chemical composition of interstellar space was fundamentally different. 3I/Atlas is essentially a fossil from the galaxy's Middle Age, explains Dr. Rosemary Wise from Johns Hopkins University. By studying its composition, we can learn about planetary formation processes during an era when the galaxy was more chemically primitive than it is today. This temporal perspective is crucial for understanding how planetary systems have evolved over cosmic time. The building blocks available for planet formation 7 billion years ago were different from what's available today, potentially leading to planetary systems with different compositions and characteristics than more recently formed systems like our own. Implications for exoplanet science. The information encoded in 3I/Atlas has direct relevance for our understanding of the thousands of exoplanets discovered by space telescopes like Kepler and TESS. While these missions can detect exoplanets and determine some of their basic properties, they can't provide detailed information about planetary composition or the materials available during planet formation. 3I/Atlas offers a different approach: direct sampling of materials from exoplanetary systems. If we can identify the stellar type and formation environment where 3I/Atlas originated, we can use this information to better understand what types of materials are available for planet formation around similar stars. 3I/Atlas is like having a sample return mission to an exoplanetary system, says Dr. Sarah Seeger from MIT. Instead of just inferring planetary properties from distant observations, we can actually analyze materials from other star systems in our own laboratories. It's a completely different approach to exoplanet science. The search for biosignatures. Perhaps the most exciting possibility is that 3I/Atlas might carry traces of biological activity from its birth system. While the probability is extremely low, the potential for detecting biosignatures, chemical markers that could indicate past or present life, makes every measurement precious. Organic compounds that could serve as biosignatures include amino acids, complex hydrocarbons, and specific molecular chirality, handedness, that's often associated with biological processes. Advanced mass spectrometry techniques being applied to 3I/Atlas's outgassing could potentially detect these compounds if they're present. We're not expecting to find little green men in 3I/Atlas, clarifies Dr. Jennifer Eigenbrode from NASA Goddard. But if its birth system ever harbored life, there's a tiny possibility that molecular fossils or biomarkers could have been incorporated into the materials that eventually became this comet. It's a long shot, but the implications would be so profound that we have to look. Building a database of alien worlds. As we detect more interstellar visitors, we'll begin building a database of materials from different stellar environments throughout our galaxy. Each visitor carries samples from a different source, gradually building our understanding of the diversity of planetary formation processes around different types of stars. In the future, we might be able to create a kind of geological survey of our galaxy, envisions Dr. Matthew Knight from the Naval Research Laboratory. Each interstellar visitor would add another data point, helping us understand the full range of conditions and materials available for planet formation throughout the Milky Way. 3I/Atlas represents just the beginning of this cosmic geological survey. As more interstellar visitors are discovered and studied, we'll develop an increasingly sophisticated understanding of how planetary systems form, evolve, and exchange materials throughout our galactic neighborhood. Hunting for life's building blocks. The search for life beyond Earth has traditionally focused on detecting habitable planets around distant stars or listening for radio signals from alien civilizations. But 3I/Atlas offers a completely different approach to astrobiology. The possibility that the building blocks of life, or even life itself, might be delivered to our doorstep aboard interstellar visitors. This isn't science fiction. It's based on a serious scientific concept called panspermia, the idea that life, or at least its chemical precursors, might spread throughout the galaxy via natural processes. Interstellar objects like 3I/Atlas could serve as cosmic arc ships, carrying organic compounds and potentially even dormant microorganisms between star systems across vast stretches of space and time. The chemistry of life in space. Life as we know it depends on complex organic chemistry, intricate molecules based on carbon that can store information, catalyze reactions, and self-replicate. For decades, astronomers have been discovering these compounds throughout the cosmos, from the atmospheres of distant exoplanets to the vast molecular clouds where stars are born. 3I/Atlas provides a unique opportunity to study organic chemistry that formed around another star and survived a billion-year journey through interstellar space. The preliminary spectroscopic analysis has already revealed signatures consistent with complex carbon-bearing compounds, but identifying specific molecules requires much more detailed investigation. Dr. Stephanie Millam from NASA Goddard Space Flight Center leads efforts to identify organic compounds in cometary material. What makes 3I/Atlas so exciting from an astrobiological perspective is that it's essentially a flying chemistry lab from another star system. Any organic compounds we detect represent chemistry that occurred under different conditions than what we see in our solar system. The most promising targets for detection include amino acids, the building blocks of proteins, and nucleotide bases that form the foundation of DNA and RNA. While finding these specific compounds would be extraordinary, even simpler organic molecules would provide valuable insights into the potential for complex chemistry in other planetary systems. Survival in the cosmic deep. One of the biggest challenges for the panspermia hypothesis has been whether delicate organic compounds, and especially living organisms, could survive the harsh conditions of interstellar space. The environment between stars is hostile to life as we know it. Temperatures just a few degrees above absolute zero, intense cosmic radiation, and a near-perfect vacuum that would be instantly lethal to most Earth organisms. But 3I/Atlas provides encouraging evidence that at least some organic chemistry can survive these conditions. The object has been wandering through interstellar space for potentially billions of years, yet it still contains complex compounds that are sensitive to radiation damage. Dr. Christopher Chiba from Princeton University, who studies the survival of organics in space environments, explains the protective mechanisms. Large objects like 3I/Atlas can actually shield their interior materials from cosmic radiation. The outer layers get processed and altered, but the interior can remain relatively pristine. Think of it like a cosmic refrigerator with built-in radiation shielding. Laboratory experiments have shown that some hardy microorganisms can survive conditions similar to those in interstellar space, at least for limited periods. Extremophile bacteria that live in Earth's most hostile environments, from the radioactive cores of nuclear reactors to the frozen soils of Antarctica, demonstrate that life can be remarkably resilient. The deep freeze advantage. The extreme cold of interstellar space, while lethal to most life, actually provides an advantage for preserving organic compounds and potentially even dormant organisms. At temperatures just a few degrees above absolute zero, chemical reactions essentially stop, creating perfect preservation conditions. Interstellar space is like the ultimate deep freeze, explains Dr. Francis Westall from the Centre de Biophysique Moléculaire. Any organic compounds or microorganisms trapped in the interior of an object like 3I/Atlas would be preserved in suspended animation for billions of years. When the object finally approaches a star and heats up, these materials could potentially become active again. This preservation effect has been demonstrated in Earth's polar regions, where microorganisms have been revived after being frozen for hundreds of thousands of years. If similar preservation is possible in interstellar space, then objects like 3I/Atlas could potentially carry viable biological material between star systems, searching for molecular fossils. Even if 3I/Atlas doesn't contain living organisms, it might carry what astrobiologists call molecular fossils, complex organic compounds that could only have been produced by biological processes. These biosignatures could provide evidence that life existed in its birth system billions of years ago. The search for these molecular fossils requires incredibly sensitive analytical techniques. Mass spectrometry can identify specific organic compounds down to parts per billion concentrations. Chirality measurements can detect the handedness of organic molecules that often indicates biological origin. Isotopic analysis can reveal the chemical pathways through which compounds were formed. Dr. Daniel Glavin from NASA Goddard, who has spent decades searching for biosignatures in meteorites, describes the challenge. We're looking for needles in a cosmic haystack. The organic compounds we're seeking might represent less than 1 part per million of the total material in 3I/Atlas. But if we find them, they could represent the first direct evidence of chemistry associated with life in another star system. The contamination challenge. One of the biggest challenges in searching for biosignatures in 3I/Atlas is avoiding contamination from Earth-based sources. Our planet is covered with organic compounds and teeming with microorganisms that could easily contaminate samples if proper precautions aren't taken. This means that any direct sampling of 3I/Atlas material would need to follow protocols even more stringent than those used for Mars sample return missions. The samples would need to be collected in sterile conditions and analyzed in ultra-clean laboratory environments designed to detect and eliminate any possible Earth-based contamination. The irony is that Earth is so rich in organic chemistry that it's actually difficult to study extraterrestrial organics here. Notes Dr. Jason Dworkin from NASA Goddard. We have to be incredibly careful to distinguish between compounds that came from 3I/Atlas and compounds that came from Earth's biosphere. Distribution mechanisms. If life or its building blocks can indeed spread between star systems via interstellar objects, the implications for the prevalence of life in the galaxy are profound. Rather than life emerging independently on each world, biological complexity could be shared and distributed throughout our galactic neighborhood. Computer simulations suggest that our galaxy has exchanged trillions of objects between star systems over its 13 billion-year history. If even a tiny fraction of these objects carried viable biological material, life could have spread to virtually every star system in the galaxy. The galactic environment might be much more interconnected biologically than we've ever imagined, speculates Dr. Edward Bell Bruno from Princeton University. If panspermia operates on galactic scales, then life might be a community property rather than something that evolves independently on isolated worlds. Earth as a target. The recognition that interstellar objects regularly visit our solar system raises fascinating questions about Earth's own biological history. Could some of the organic compounds essential for life on Earth have originally arrived aboard interstellar visitors billions of years ago? While Earth clearly has its own robust chemistry for producing organic compounds, interstellar delivery could have supplemented local production or provided specific molecules that were crucial for the emergence of life. Some of the organic compounds found in Earth's oldest rocks might actually be interstellar in origin. We may owe more to interstellar visitors than we realize, suggests Dr. David Deemer from UC Santa Cruz. The early Earth was bombarded by materials from throughout the solar system and probably from interstellar space as well. Some of the key ingredients for life might have been delivered from other star systems. Future opportunities. As our detection capabilities improve and we discover more interstellar visitors, the opportunities for astrobiological studies will multiply. Each new object represents a potential sample from a different stellar environment, gradually building our understanding of organic chemistry throughout the galaxy. The ultimate goal would be to actually intercept and sample an interstellar visitor before it's been altered by heating from our Sun. ESA's Comet Interceptor mission, launching in 2029, represents the first serious attempt to rendezvous with an interstellar object, though the probability of finding a suitable target is low. Every interstellar visitor is a potential biology experiment from another star system, says Dr. Lynn Rothschild from NASA Ames. As we get better at detecting and studying these objects, we're opening up entirely new ways to search for life beyond Earth. Instead of trying to travel to other star systems, we're letting them come to us. The study of 3I/Atlas represents just the beginning of this new approach to astrobiology. Whether or not it carries direct evidence of life from its birth system, it's already expanding our understanding of how organic chemistry develops around other stars and how biological materials might spread throughout our galaxy. In the coming decades, as more interstellar visitors arrive bearing samples from distant worlds, we may finally answer the profound question of whether life is a unique cosmic accident or a galactic phenomenon that connects star systems throughout the Milky Way. The golden age of interstellar discovery. We are living through the opening moments of what future historians will call the golden age of interstellar discovery. The detection of 3I/Atlas in July 2025 wasn't just another astronomical discovery. It was the moment humanity gained the technological capability to routinely detect, track, and study visitors from other star systems. We're transitioning from a world where interstellar objects are rare, lucky finds to one where they become regular scientific targets. This transformation is happening right now, powered by a perfect storm of technological advances that are revolutionizing our ability to scan the cosmos. The Vera C. Rubin Observatory, which achieved first light just months before 3I/Atlas was discovered, represents the vanguard of this revolution. Picture this: every 3 nights, the Rubin Observatory will photograph the entire southern sky with its 8.4-meter telescope and 3.2 gigapixel camera, the largest digital camera ever constructed for astronomy. In a single image, this camera captures an area of sky 40 times larger than the full moon, with resolution so fine it could spot a golf ball from 15 miles away. Dr. Mario Jurek from the University of Washington, who leads the Rubin Observatory's data management team, describes the scope. Over its 10-year survey, Rubin will generate 60 petabytes of data, roughly equivalent to streaming 13 million movies in 4K resolution. Every night, we'll detect and measure 20 million objects, tracking everything that moves, changes brightness, or appears in the sky. But the real revolution isn't just in the hardware. It's in the artificial intelligence systems that will process this astronomical fire hose of information. Machine learning algorithms trained on millions of known objects can now identify interstellar visitors in real time, flagging them for immediate follow-up observations before they disappear back into the cosmic dark. The numbers game. Conservative estimates suggest the Rubin Observatory will discover 1 to 3 Oumuamua-sized interstellar objects per year during its survey. But these projections might be dramatically underestimating what's coming. The discovery rate depends on factors we're still learning about. How common are interstellar objects? What size distribution do they follow? How many approach from directions and distances that make them detectable? Dr. Matthew Holman from the Harvard-Smithsonian Center for Astrophysics has modeled various scenarios. If interstellar objects follow the same size distribution as comets in our solar system, Rubin could detect dozens per year. If they're more common than current estimates suggest, we could be looking at hundreds of discoveries annually. Even more exciting are the projections for smaller objects. Rubin's sensitivity will extend to objects just a few hundred meters across, roughly the size of a large building. For the first time, we'll be able to detect and study the small interstellar debris that probably represents the vast majority of material flowing between star systems. We're about to discover that our solar system is absolutely teeming with interstellar visitors, predicts Dr. Alan Stern from the Southwest Research Institute. What we've seen so far with Oumuamua, Borisov, and 3I/Atlas is just the tip of an enormous iceberg. Beyond Earth-based surveys, the revolution in interstellar object discovery isn't limited to ground-based telescopes. Space-based surveys are beginning to contribute their own unique advantages, including the ability to observe continuously without weather interference and access to wavelengths blocked by Earth's atmosphere. The James Webb Space Telescope, while primarily designed for deep space observations, has already demonstrated its ability to study interstellar visitors in unprecedented detail. Its infrared instruments can detect the thermal emission from these objects, providing information about their size, shape, and composition that's impossible to obtain from visible light alone. Future space missions specifically designed for solar system surveillance will further multiply our detection capabilities. The NEO Surveyor mission, launching in the late 2020s, will scan the sky for potentially hazardous asteroids, but will also be perfectly positioned to spot interstellar visitors approaching from the sun's direction, a blind spot for ground-based telescopes. We're building a comprehensive surveillance network that will eventually have coverage of the entire sky, 24 hours a day, across multiple wavelengths, explains Dr. Amy Mainzer from the University of Arizona, who leads the NEO Surveyor mission. Interstellar objects won't be able to slip through undetected much longer. The International Response Network. As interstellar object discoveries become routine, the astronomical community is developing rapid response protocols that can mobilize telescopes worldwide within hours of a detection. The success of the 3I/Atlas observational campaign demonstrated what's possible when the global astronomy community coordinates effectively. The International Astronomical Union has established the Interstellar Object Working Group, which coordinates follow-up observations and maintains databases of interstellar visitor properties. When a new object is discovered, automated alerts go out to observatories on every continent, triggering a coordinated campaign to extract maximum scientific value before the visitor disappears. We've learned that every interstellar object represents a unique scientific opportunity that we can't afford to waste, says Dr. Michelle Bannister from the University of Canterbury. These objects are cosmic messengers that carry irreplaceable information about conditions throughout our galaxy. Once they're gone forever. The Rapid Response Network includes not just professional observatories, but also thousands of amateur astronomers equipped with increasingly sophisticated equipment. The Interstellar Citizen Science Network, which successfully tracked 3I/Atlas, is expanding rapidly and developing new protocols for distributed observations of faint, fast-moving targets. Artificial intelligence as co-discoverer. Perhaps the most transformative aspect of the coming golden age is the role of artificial intelligence as a full partner in scientific discovery. AI systems are no longer just tools for processing data. They're becoming autonomous discoverers that can identify patterns and anomalies beyond human capability. Machine learning algorithms trained on simulated populations of interstellar objects can now predict the most likely discovery locations and times, allowing surveys to optimize their search strategies. These systems can distinguish between genuine interstellar visitors and the countless solar system objects that contaminate the search space. We're entering an era where AI systems will be making discoveries faster than human astronomers can follow up on them, predicts Dr. John Tonry from the University of Hawaii. The bottleneck is shifting from detection to detailed characterization and understanding. Advanced AI is also revolutionizing how we analyze interstellar objects once they're discovered. Neural networks can extract compositional information from low-resolution spectra, predict object behavior based on limited observations, and even identify potential targets for spacecraft intercept missions. Missions to intercept. The ultimate goal of interstellar object science is to get up close and personal with these cosmic visitors. ESA's Comet Interceptor mission, launching in 2029, represents humanity's first serious attempt to rendezvous with an interstellar object. The mission design is elegant in its simplicity. 3 spacecraft will position themselves at the Sun-Earth L2 point and wait for a suitable target to be discovered. When an interesting interstellar visitor is detected with enough advance warning, the spacecraft will launch an intercept mission to study it up close. Comet Interceptor is designed for the unknown, explains Dr. Geraint Jones from the Mullard Space Science Laboratory, the mission's deputy principal investigator. We don't know what type of interstellar object we'll encounter, so the spacecraft carry a comprehensive suite of instruments capable of studying everything from rocky asteroids to active comets. The probability of Comet Interceptor finding a suitable interstellar target is estimated at only about 7%. But the mission represents proof of concept for future, more capable interceptor missions. If successful, it will provide the first close-up data on an interstellar visitor, revealing details about internal structure, composition, and formation history that are impossible to determine from Earth-based observations. Next-generation missions. Even more ambitious missions are already in the planning stages. The Bridge mission concept would deploy multiple interceptor spacecraft throughout the solar system, stationed at strategic points to maximize the probability of encountering interesting targets. Advanced propulsion systems using ion drives or even solar sails could enable these spacecraft to chase down and rendezvous with fast-moving interstellar visitors. Dr. Robert Warwick, who discovered Oumuamua, envisions an even more ambitious approach. Imagine a network of small, intelligent spacecraft distributed throughout the solar system, each capable of autonomously detecting and intercepting interstellar objects. We could study dozens of these visitors up close, building a comprehensive database of materials from throughout our galaxy. The technological challenges are substantial. Interstellar objects move at speeds of 30 to 60 kilometers per second, requiring precise navigation and timing to achieve successful rendezvous. But the scientific payoff would be revolutionary, providing direct samples from alien worlds for detailed laboratory analysis on Earth. The questions 3I/Atlas raises. While 3I/Atlas has answered some fundamental questions about interstellar visitors, it has raised even more profound mysteries that will drive astronomical research for decades to come. Each new piece of data about this ancient cosmic wanderer reveals new puzzles about the nature of planetary systems, galactic evolution, and the distribution of materials throughout the universe. The Age Paradox. Perhaps the most perplexing mystery about 3I/Atlas concerns its remarkable preservation despite its estimated 7 billion-year age. How has this object managed to retain pristine water ice and organic compounds while drifting through the harsh environment of interstellar space for longer than our solar system has existed? The radiation environment between stars should gradually break down complex molecules and sublime volatile ices over such vast timescales. Cosmic rays, high-energy particles that permeate the galaxy, should have penetrated deep into 3I/Atlas and altered its chemistry throughout. Yet spectroscopic analysis suggests the object contains remarkably fresh materials. Dr. Alan Stern from the Southwest Research Institute frames the paradox. It's like finding a perfectly preserved ice cube that's been sitting in a desert for millions of years. The preservation of volatiles in 3I/Atlas over billions of years challenges our understanding of how materials behave in interstellar space. Several theories attempt to explain this preservation mystery. Perhaps 3I/Atlas spent most of its journey in unusually benign regions of interstellar space, avoiding the most radiation-rich environments. Maybe its large size provided effective self-shielding, with the outer layers protecting interior materials from cosmic ray damage. Alternatively, 3I/Atlas might not be as old as initial estimates suggest. The trajectory analysis that points to galactic thick disk origins could be misleading if the object has experienced unknown gravitational encounters that altered its path. Determining the true age and journey history of 3I/Atlas remains one of the most challenging puzzles in interstellar object science. The origin mystery. While astronomers can trace 3I/Atlas's trajectory back toward the galactic thick disk, identifying its specific birth system remains an unsolved challenge that may be impossible to definitively answer. The galactic thick disk contains billions of stars, many of which have completed dozens of orbits around the galaxy since 3I/Atlas began its journey. The stars that were 3I/Atlas's neighbors 7 billion years ago are now scattered across thousands of light-years. Some may have died in supernovae explosions. Others have been gravitationally scattered into different parts of the galaxy. The specific planetary system where 3I/Atlas formed may no longer exist in any recognizable form. It's like trying to identify a specific tree in a forest that was chopped down and replanted multiple times over billions of years, explains Dr. Rosemary Wise from Johns Hopkins University. The galactic neighborhood has been completely reshuffled since 3I/Atlas began its journey. This origin mystery has profound implications for understanding galactic dynamics and stellar evolution. If we could identify 3I/Atlas's birth system, we might learn about planetary formation processes around ancient stars and how stellar systems evolve over cosmic timescales. Advanced stellar archaeology techniques might eventually provide clues. By analyzing the isotopic composition of materials in 3I/Atlas and comparing them to spectroscopic surveys of thick disk stars, astronomers might be able to narrow down the type of stellar environment where it originated, even if they can't identify the specific star. The composition enigma. The chemical makeup of 3I/Atlas raises fundamental questions about planetary formation processes around other stars. Why does it contain such abundant water ice when objects from the cold outer regions of planetary systems typically show more complex ice compositions including carbon monoxide, methane, and other volatiles? The dominance of water ice in 3I/Atlas's coma suggests formation conditions that were different from what we observe in our own solar system's comet populations. This could indicate that planetary systems around thick disk stars developed under different chemical and thermal conditions than more recently formed systems. The composition of 3I/Atlas doesn't quite match what we'd expect from any specific formation environment we know about, notes Dr. Stefano Bagnolo from the Armagh Observatory. It's like finding a geological sample that doesn't fit into any known category of rock formation. It suggests there are planetary formation processes we don't fully understand. Understanding this compositional puzzle requires more detailed spectroscopic analysis as 3I/Atlas continues to approach the Sun and becomes more active. Different ice species sublime at different temperatures, so the changing composition of the coma as the object heats up will reveal the layered structure of its nucleus. The activity anomaly. Another puzzling aspect of 3I/Atlas is the specific pattern of its cometary activity. As it approaches the Sun, it's releasing water vapor and dust at rates that are higher than expected for an object of its estimated size and composition. This suggests either that 3I/Atlas is larger than current estimates or that it has unusually high volatile content. The dust-to-gas ratio in 3I/Atlas's coma also differs from typical solar system comets, indicating different formation or evolution processes. Understanding why interstellar visitors show different activity patterns than local comets could reveal fundamental differences between planetary formation around ancient versus modern stars. Dr. Nalin Samarasinha from the Planetary Science Institute describes the challenge. 3I/Atlas is behaving like a comet, but not quite like any comet we've studied before. The specific patterns of gas and dust release suggest internal structure or composition that's unlike anything in our local cosmic neighborhood. The population statistics problem. The discovery of 3 interstellar objects in just 8 years has revolutionized estimates of how common these visitors are, but major questions remain about the overall population statistics. Are Oumuamua, Borisov, and 3I/Atlas representative of typical interstellar visitors, or are they unusual objects that don't reflect the broader population? Each of our 3 detected visitors has been different enough to suggest we're sampling from a very diverse population. But with only 3 examples, it's impossible to determine which properties are common and which are rare among interstellar objects. We're trying to understand the ecology of an entire ecosystem based on 3 specimens, explains Dr. Matthew Holman from Harvard-Smithsonian. It's like trying to understand all of Earth's animals by studying a penguin, a butterfly, and an elephant. You'd know there's diversity, but you'd have no idea about the millions of other species. The coming flood of discoveries from next-generation surveys will begin to answer these statistical questions, but fundamental uncertainties will persist until we have hundreds or thousands of detected interstellar visitors to analyze. The survival paradox. A deeper mystery concerns how objects like 3I/Atlas survive their billion-year journeys through interstellar space at all. The galaxy is a violent place, filled with stellar explosions, gravitational disruptions, and high-energy radiation. Most small objects should be destroyed or dramatically altered during such extended exposure to galactic hazards. Yet 3I/Atlas appears to have survived essentially intact, retaining both its physical structure and chemical composition. This suggests either that interstellar space is less hostile than theoretical models predict, or that there are protective mechanisms we don't understand. The very existence of well-preserved interstellar objects like 3I/Atlas challenges our understanding of galactic evolution, says Dr. Ruth Murray Clay from UC Santa Barbara. These objects have survived conditions that should have destroyed them multiple times over. Something is protecting them, and we don't know what. The detection bias dilemma. Perhaps the most troubling question is whether our current detection methods are giving us a representative sample of interstellar visitors or are biased toward specific types of objects. All 3 confirmed interstellar objects were detected when they were relatively close to the Sun and showing some level of activity. This means we might be systematically missing entire categories of interstellar visitors. Objects that stay in the outer solar system, completely inactive objects that don't outgas, or objects that approach from directions our surveys don't monitor effectively. We're like fishermen who only cast nets in shallow water and then wonder why we're not catching deep-sea fish, admits Dr. Robert Warwick. Our detection methods have built-in biases that could be hiding entire populations of interstellar objects. Understanding and correcting for these detection biases is crucial for accurately estimating the true frequency and diversity of interstellar visitors. Future surveys with broader coverage and higher sensitivity will help address some of these limitations, but fundamental biases may persist. Why this changes everything? The discovery and study of 3I/Atlas represents more than just finding another interesting cosmic object. It fundamentally alters humanity's understanding of our place in the universe and opens entirely new perspectives on life, planetary formation, and galactic evolution. This single ancient visitor from the galactic thick disk has rewritten textbooks and shifted the entire framework of how we think about our cosmic neighborhood. Redefining solar system boundaries. Before the interstellar object discoveries, we thought of our solar system as a discrete, isolated unit with clear boundaries defined by the Sun's gravitational influence. The detection of regular interstellar visitors has shattered this provincial view, revealing that our solar system is actually an open system in constant communication with the rest of the galaxy. 3I/Atlas and its predecessors prove that materials flow freely between star systems throughout the Milky Way. Our solar system isn't an island, it's more like a port city where cosmic trade routes converge, constantly receiving shipments of materials from distant worlds and sending its own exports into the galactic marketplace. The traditional view of isolated solar systems is dead, declares Dr. Alan Stern. We now know that planetary systems throughout the galaxy are all connected through the exchange of materials. It's a much more dynamic and interconnected universe than anyone imagined. This connectivity has profound implications for understanding planetary formation and evolution. The materials that built Earth and the other planets in our solar system might not have originated entirely from our local stellar environment. Some fraction could have been imported from other star systems, carrying information about planetary formation processes around very different types of stars. A new branch of astronomy, the study of interstellar objects, has created an entirely new scientific discipline that combines aspects of planetary science, stellar astronomy, galactic dynamics, and astrobiology. This field, sometimes called galactic archaeology or interstellar planetary science, uses visitors like 3I/Atlas as natural space probes carrying samples from throughout the galaxy. Dr. Jennifer Bergner from UC Berkeley, whose work helped solve the Oumuamua mystery, describes the revolutionary nature of this new field. We're doing planetary science on worlds we'll never visit, around stars we may never identify. Every interstellar visitor is a sample return mission from an alien world, delivered free of charge to our cosmic doorstep. This approach to studying exoplanets offers advantages that traditional methods can't match. Instead of inferring planetary properties from subtle changes in starlight, scientists can directly analyze materials from other worlds in Earth-based laboratories using the most sophisticated analytical techniques available. The astrobiology revolution. Perhaps nowhere is the impact of interstellar object discoveries more profound than in astrobiology, the search for life beyond Earth. The recognition that organic compounds can survive billion-year journeys between star systems opens up entirely new possibilities for how life might spread throughout the galaxy. If microorganisms can survive the journey aboard interstellar visitors, then life itself might be a galactic phenomenon rather than something that emerges independently on isolated worlds. This version of panspermia would mean that all life in our galaxy could be related, sharing a common ancestor that spread between star systems over billions of years. 3I/Atlas could literally be carrying our cosmic cousins, speculates Dr. Lynn Rothschild from NASA Ames. If life can survive interstellar travel, then biology might be a galactic community property rather than isolated experiments happening on individual worlds. Even if interstellar objects don't carry living organisms, they certainly transport the chemical building blocks of life. The organic compounds detected in comets like Borisov and potentially in 3I/Atlas demonstrate that the raw materials for biology are distributed throughout the galaxy via natural processes. Transforming planetary defense. The discovery that thousands of interstellar objects are constantly passing through our solar system has added new complexity to planetary defense efforts. While the vast majority of these visitors pose no threat to Earth, the possibility of a dangerous interstellar impactor can't be completely dismissed. Interstellar objects approach at much higher speeds than typical solar system asteroids, often 2 to 3 times faster. This means less warning time if one were on a collision course with Earth, and deflection missions would be more challenging due to the extreme approach velocities. We're not losing sleep over interstellar impactors, clarifies Dr. Kelly Fast from NASA's Planetary Defense Office, but they represent a new category of potential threat that we need to understand and prepare for. The positive aspect is that our rapidly improving detection capabilities mean we'll likely spot any dangerous interstellar visitor long before it poses a threat. The same surveys that are revolutionizing interstellar object science are also making Earth safer by providing earlier warning of potential impactors. Economic and technological implications. The study of interstellar objects is driving technological innovations with applications far beyond astronomy. The AI systems developed for automated object detection are finding uses in medical imaging, autonomous vehicles, and industrial quality control. Advanced spectroscopic techniques for analyzing faint cosmic objects are being adapted for environmental monitoring and materials science. More speculatively, interstellar objects might eventually become targets for resource extraction. Objects like 3I/Atlas contain vast quantities of water ice and potentially rare elements that could be valuable for space-based industries. While the technology for intercepting and mining interstellar visitors is still decades away, the concept represents a new frontier for space commerce. Interstellar objects are like cosmic or deposits, suggests Dr. John Lewis from the University of Arizona. They're carrying concentrated materials from throughout the galaxy directly to our solar system. Future space industries might find it easier to intercept these natural deliveries than to mine asteroids or travel to other star systems. Philosophical and cultural impact. Beyond the scientific and technological implications, the discovery of regular interstellar visitors has profound philosophical significance for humanity's understanding of our cosmic context. We are not alone in an empty universe. We are part of a vast galactic ecosystem where materials and possibly even life flow freely between worlds. This realization is changing how we think about Earth's place in the cosmos. Our planet isn't an isolated oasis in a cosmic desert. It's a member of a galactic community that includes billions of other worlds, all connected through the natural processes that transport materials between star systems. Finding that we're surrounded by visitors from other worlds changes the entire human perspective on our place in the universe. Reflects Dr. Sarah Seeger from MIT. We're not alone and never have been. We're part of a galactic family that's been exchanging materials and possibly even life for billions of years. The future of human exploration. The knowledge that interstellar objects regularly visit our solar system is also influencing long-term planning for human space exploration. Instead of thinking about expensive, multi-generational missions to nearby star systems, we might be able to study materials from throughout the galaxy without leaving our cosmic neighborhood. Future space missions could intercept interstellar visitors and return samples to Earth for detailed analysis. This would provide direct access to materials from dozens or hundreds of different stellar systems, creating a comprehensive survey of planetary formation processes throughout our galaxy. Why travel to other star systems when other star systems are coming to us? Asks Dr. Robert Warwick. Interstellar objects offer a much more cost-effective way to explore the galaxy than building interstellar spacecraft. A new cosmic perspective. The cumulative impact of discovering regular interstellar visitors extends far beyond any single scientific discovery. It represents a fundamental shift in how humanity understands its place in the cosmos, from isolated residents of a single star system to citizens of a vast galactic community where materials, energy, and possibly even life flow freely between worlds. 3I/Atlas, carrying samples that predate our solar system by billions of years, serves as a tangible reminder that our cosmic story extends far beyond our local environment. We are literally made of star stuff, as Carl Sagan famously said, but now we know that some of that star stuff might have originated in very different stellar environments than our own sun. Every time we look at 3I/Atlas, we're seeing a piece of the galaxy's ancient history, says Dr. Michelle Bannister. It's a cosmic archaeology artifact that connects us to stellar systems that existed when our galaxy was young. In studying these visitors, we're not just doing astronomy, we're tracing our cosmic family tree. The story of 3I/Atlas is ultimately the story of connection between star systems, between different epochs of galactic evolution, and between humanity and the vast cosmos that surrounds us. As we continue to study this ancient messenger and the many interstellar visitors that will follow, we're not just learning about distant worlds. We're discovering the cosmic processes that shaped our own existence and continue to link our fate to the broader galactic community. The age of interstellar archaeology has begun, and 3I/Atlas is our first glimpse into a universe far more interconnected and dynamic than we ever dared to imagine. In the words of the Hawaiian astronomers who named our first interstellar visitor, these objects are truly Oumuamua messengers from afar, arriving to tell us that we are not alone in the cosmic dark, but part of a vast galactic family that has been sharing materials and stories across the light years for billions of years. Our cosmic perspective will never be the same.